Welcome to Physics 123, lab number 3. This is resonant standing sound waves. And today we're going to be looking at, similar to the previous lab, how we had resonance in standing waves in a wire, except this time we're going to be examining longitudinal sound waves and when they are in resonance. Okay, so the equipment that we're going to be using for this lab is this pipe. It's just a clear, airtight pipe. And at one end, we have a speaker. And this speaker is connected to a sine wave generator. And when we plug this in, it will produce a sine sound wave input to the speaker, which will then come out of the speaker here. And then these sound waves, these longitudinal air waves, which we know is sound, will come down the pipe. And then it'll reflect off this stopper here. And this stopper we can adjust, and you can even hear it when we have resonance. The amplitude of the sound, the like decibel level, audibly goes up. And so we can adjust this and find where there's resonance, and then just measure this distance here. And that is from that distance we can find a lot of cool things like the wavelength of the sound waves. Okay, so here we have the sine wave generator set at 700 hertz. So you'll want to notate that. And what we're going to do is we're just going to pull back the stopper to change the effective length of the tube and look for, listen for resonance where we hear the amplitude of the sound waves go up. So this, if you could, maybe I'll go back and just listen. Just try to hear where the sound seems louder, and once it's louder I'll try to position the stopper there, and then we can measure that. Okay, so it seems like that is pretty loud compared to the other ones, and so this is where we have a resonance peak. And so if we grab this ruler, we're going to measure this distance labeled L from the start of the tube to where the stopper is. And so take that value down. And that's your first resonant length. And now we can move on to find the second one. We can hear the sound decrease quite drastically when we move out of that resonance. Here it's hard to pick up. I'll go a little bit past just to make sure that we're still we're right on the resonance. And then I adjust it back until it's really loud like that. And this is our second resonance length. So maybe zoom out a little bit. Okay, so that's 34-ish, 33 point something. Okay, now we're going for number 3. Quiets down when we're not in resonance. And here we are picking back up. Okay. So there's your third distance. And then we'll do one more. And those are your 4 resonant lengths. Go ahead and turn this off. That's all the data that you need for this lab. You should have, in the beginning, drawn out what the kind of in similar form as this, where you could draw what the waves would look like for the first 4 positions, and then based on that, you should be able to calculate the wavelengths. And then from there, you can just do some numeric approximation to try to compensate for this delta L here, because in all actuality, if we look down here, the speaker is not right up against to the tube. So there's some length here that the standing waves are extending out. Now it's not all the way to the speaker because it's no longer enclosed, but they are not exactly on the end here. So that delta L, you just want to numerically experiment. You know, I'd probably start with, I don't know, around a centimeter. Try varying that and seeing how your answers look. Again, you want them to be consistent, and so that's the key there. But it's, again, just using the data from before. If you do get stuck on any of the data analysis or any part of the lab here, go ahead and keep watching. We'll include a couple extra helpful hints at the end here. Okay, so one thing while you're doing the first part of this lab that you need to think about and be aware of is that at the end of the lab, or at the end of the tube here, we're always going to have an antinode, right, where it's open. And then at the end where the stopper is, we're always going to have a node, okay? And so if you think about it, the first one, the first resonance value will be where this is a node, and then the end is an antinode, right? And the second one, we have to go to the next antinode. And then you just repeat that for the first 4. So that's, in case you get stuck on the first one, that's how you need to handle that. For this part and finding the wavelengths, it's pretty straightforward. You just use the formula, right? Velocity equals frequency times wavelength. The frequency you should have recorded, and then we just recorded these L values. Now the last part is a little bit more tricky because the fact that this speaker is not right up against the end of the wave and the end of the tube means that this standing wave will actually come out of the tube a little bit, and we just measured this L was just from the end of the tube to where we had the stopper. And so really somewhere this L really should be somewhere closer outside the tube. Now it's not necessarily going to be all the way to the speaker because it is open, right? And in order to have these standing waves, we need it enclosed, and so it's just gonna, this standing wave is just really going to extend some portion out from the end of the tube to the speaker. And so what you're going to want to do is you're just going to want to, make an estimation, like 0.01 meters, and then plug that in to your values. And the key is that you want these wavelengths to be the same. And so, you try 0.01, then try 0.015 or 0.05, and just try to get a delta L that is that makes all of these wavelengths pretty close together. And so just go by your discretion what you think is correct, or at least close enough. I would try at least 3 or 4 delta L's. And if you want to know where to start, we can measure over here. And the speaker is about 1.4. So this gap is about 1.4. So that's going to be like your high end, right? It can't, this delta L kind of fudge factor is not going to be more than 1.4 centimeters long. So you can maybe start at 1, or I don't know. You pick, but this is called numeric approximation, right? We're just numerically evaluating different delta L's that we can add here and see how it affects our values. And once we get all the values to agree, that means that we have a correct delta L. And then that's what you're going to record there. So thanks and good luck.